Sodium thiosulfate reacts with dilute hydrochloric acid as shown. Give the simplest ionic equation for this reaction. So we need to remember that it's anything that is aqueous and ionic is going to be able to split into its ions. So sodium thiosulfate is aqueous and ionic. Split into sodium ions, and we've got 2 sodium ions and 1 thiosulfate ion. Hydrochloric acid is a strong acid, so fully ionizes into 2 hydrogen ions and 2 chloride ions. Sodium chloride is aqueous and ionic, and we've got 2 sodium chlorides, so we get 2 sodiums and 2 chlorides. The other 3 products are not AQ, so they are staying as they are. And then we're going to cross out anything that appears on each side, so the sodium ions and the chloride ions, so that we can see we've got the thiosulfate ions and the acid, the H+, giving us sulfur dioxide, sulfur and water. The gas SO2 is a pollutant. State the property of SO2 that causes pollution when it enters rivers. Well, SO2 is a non-metal oxides, and non-metal oxides are acidic. Metal oxides are bases, non-metal oxides are acids, and it's going to cause acid increasing acidity concentration in the water. It's going to lower the pH of the water. When it reacts with the water, it forms sulfuric 4 acid, so not the normal sulfuric acid you might have been used to seeing, but H2SO3. Draw a diagram to show the shape of a molecule of H2O. Include any lone pairs and state the bond angle and explain the shape and bond angle. So oxygen is in group 6, so 6 electrons to the valence shell. There are 2 hydrogens, each bringing 1, so that's 2 extra electrons, no charge. So we've got 8 electrons or 4 pairs in the valence shell, but only 2 atoms attached, so that is 2 bond pairs and 2 lone pairs. So if we draw our oxygen, it's based off the tetrahedral shape, but 2 of the sticks, so the 2 that would be coming in and out of the plane, are actually lone pairs. And they are going to reduce the bond angle from the usual 109.5 that you'd expect for a tetrahedral down by 2.5 degrees each to 104.5 degrees. So explain that shape. So we'd say there are 4 pairs of electrons around the oxygen, 2 bond pairs and 2 lone pairs, lone pairs repel more strongly than bond pairs. So if it had been 4 bond pairs, it would have been 109.5. But because we've got 2 lone pairs and they repel more than bond pairs, the angle is reduced from 109.5 to 104.5 degrees because those lone pairs repel more. And the next part of the question says the initial rate of reaction between sodium thiosulfate and hydrochloric acid can be monitored by measuring the time taken for a fixed amount of sulfur. And if you remember from the equation, sulfur was a solid to be produced. Describe an experiment to investigate the effect of temperature on rate of this reaction. So because we're making this solid sulfur, this is a disappearing cross reaction. We're going to mark a cross under our reaction vessel, and we're going to wait for enough sulfur to be produced to sort of disrupt or stop us from being able to see that cross. And then we will stop the stopwatch at that point. So what would we do? We need to think about our variables. We're looking at the effect of temperature. So temperature is the thing that we're changing. Temperature is our independent variable. On rate, we're going to have to measure time to find rate. So time is our dependent variable. What are our control variables? What must we control in this reaction? Well, the other things that could have affected this rate would be the concentrations and the volumes of the two reactants, sodium thiosulfate and hydrochloric acid. So we need to make sure that we use the same amount of each of those every time. So we're going to place a known volume and concentration. We don't have to be specific here, but we need to know that we would know it in our experiment, of Na2, the sodium thiosulfate, in a flask or a test tube, depends what you want to do your reaction in, some sort of container, and place on a cross. Add a known volume and concentration of hydrochloric acid and start the stopwatch or a timer. Stop the timer when the cross is no longer visible. Record the time taken for the cross to disappear. You will also need to record the temperature at which you have done this initial reaction. And it's a good idea to record the temperature before mixing and after the cross disappears, to allow the mean temperature to be calculated. And then we're going to repeat using the same volume and concentration of both the Na2S2O3, the sodium thiosulfate, and hydrochloric acid, but at a new temperature. And we're going to repeat for 5 different temperatures. That should give us enough to draw a line of best fit on a graph. So then what we're going to do is we're going to calculate 1/time as a measure of rate for each temperature. And we're going to plot a graph of rate 1/time against the temperatures that we've chosen. And that graph will look something like this. So we're going to have temperature along the bottom. We're going to have 1/time up the side. And our graph will be an exponentially increasing graph, like that.